This is one of 8,700 farms in the San Francisco Bay where the Sacramento and San Joaquin rivers meet. Because salty water is distributed to these farms further inland through these rivers and these irrigation canals, this leads to poor water infiltration and aeration due to toxic levels of sodium and chloride in soil and groundwater, making it challenging for crops to access the water and nutrients they need. To face existing water scarcity issues, farmers need to use more water to leach salt, forcing them to abandon their fields or switch to less profitable crops. So what's limiting farmers from combating these problems? One way to understand the constraints faced by modern agriculture is through Malthusian theory, which postulates that as the global population increases exponentially, food production increases linearly, leading to food insecurity, the limiting factor being the ability to produce food efficiently. Today, this limiting factor comes in the form of agricultural technology. While the potential to produce enough food exists, the ability to do so sustainably, especially under the pressures of climate change and environmental degradation, reveals 8 key industry gaps among current ag-tech solutions. But the question is, how do we farm to meet that demand in a way that's crop efficient, water conserving, and soil regenerative? Developed as a Java Android mobile app with TensorFlow Lite, Agsight is a novel SaaS business offered as a cost-effective, sensor-free, and spatial machine learning app to help under-resourced specialty crop farmers of small to medium-sized commercial orchards across central California combat water scarcity, vegetation stress, and unsustainable farming practices via near real-time monitoring algorithms in 3 ways: stress diagnoses from plant diseases, pests and nutritional deficiency indicators, personalized irrigation automation, and soil fertility monitoring. Upon inputting our farm's details, the app gathers 3 crucial data points that informs the rest of its features: farm's location, the crops grown, and the field or plot where they're grown. Using a convolutional neural network to classify different types of plots, segment them from satellite images of the location, we can drag and drop our crops into their corresponding plots. After logging in, we can see a detailed breakdown of the crops in each plot by aggregating location-specific geospatial and remote sensing data, which are used as features for either mathematical calculations or computer vision deep learning models. The app calculates and visualizes metrics for crop phenology, vegetative health, hydration, photosynthetic productivity, and microclimatic variations in land surface temperatures across different scales of analysis to help farmers maximize their yield. The app allows us to take a photo and automatically diagnose any plant disease using a deep convolutional neural network and data of over 40,000 images of plant leaves using multi-class classification. When initial results report, I applied image augmentation to diversify the dataset and improve predictive accuracy by 17%. When the confidence is above the set threshold, it recommends what specific actions we should take by assessing visual indicators of vegetation, nutrition, and water stress to try and predict the root causes and future development. Similarly, the water feature estimates the water, crop rotation, soil moisture requirements of each crop and plot using evapotranspiration data to provide personalized irrigation schedule that tells farmers exactly when, where, and how to deliver the right amount of water directly to the root zone of their crop to reduce water wastage by detecting early signs of water stress, so they know exactly when to apply soil amendments such as irrigation levels or implement crop rotation strategies. For soil, the app integrates USDA NCRS web soil survey data to gauge health, nutrition, moisture, acidity, and organic matter content based on the soil type and climate to recommend fertilizers, soil treatments, and crop rotation strategies. Similar to the plant diagnostic, we can scan a soil sample and get a diagnosis which uses a CNN for feature extraction from standardized and augmented soil images, followed by classification by a support vector machine that assesses soil health by correlating these visual inputs with chemical and physical soil properties. So far, results have been promising. Agsight is currently being trialed in 12 California farms. We're seeing an average yield improvement of 4.5% and a 31% decrease in crop stress-related instances, including salinization with a 98.6% accuracy compared to ground truth sensor data.